Hey there, Chem Squad. Today we're going to look at defining acids and bases. Now, in the past, we've always looked at acids as having hydrogens and bases having hydroxides. But over the years, that alone was not enough to define every acid and every base, because they all have slightly different properties and there are some special conditions. As a result, we now have three different ways of looking at acids and bases, and we'll take a look at all of them today. So the first one is called Arrhenius acids and bases. Arrhenius acids and bases are typically used to describe most of our common acids and bases. So let's just start with Arrhenius. So I'll start with the acids first, and then I'll get into the bases second. They're usually based on similar principles, okay, with a few modifications. So let's take a look at a common acid that we both know, our friend HCl, hydrochloric acid. When hydrochloric acid dissociates, it produces H plus ions as well as Cl negative ions. All of them are aqueous. Under Arrhenius' definition of an acid, all acids produce H plus ions when dissolved in water. This seems to work quite well with a majority of our strong acids, such as HCl. It also works with our weak acids, such as acetic acid or vinegar. When we dissolve that in water, we also make H plus ions, as well as anions. So both of these fit in nicely with Arrhenius' definition of what an acid is supposed to be. Now, for bases, it's not that much different. An Arrhenius base is simply a substance where if we can take, let's give you MgOH2. This is a strong base called magnesium hydroxide. And when we add water to dissolve it, it produces Mg2 plus ions, and it produces hydroxide ions. So according to Arrhenius, any Arrhenius base, or virtually all Arrhenius bases, produce hydroxide ions when dissolved in water. So what we're really looking at here is the presence of hydrogen and the presence of hydroxide, okay, for our acids and for our bases respectively. Everything would be fine except when it comes to the bases, okay? As I mentioned before, your Arrhenius base, okay, magnesium hydroxide, sodium hydroxide, aluminum hydroxide, anything that has a hydroxide is considered to be a very strong base. So strong bases work well. However, weak bases do not. So for example, consider this weak base. this is carbonate. It is considered to be a weak base compared to strong bases such as all your hydroxide compounds. Okay, this weak base, when you dissolve it in water, it doesn't break up into hydroxide ions. Okay, so it doesn't form OH ions. Therefore, is not an Arrhenius base. Okay, so we'll put in brackets Arrhenius base because it is still a base. Okay, it's just not an Arrhenius base. So one of the things that we look at now is, well, how can we reorganize the way that we define acids and bases so that we can include more substances? Okay, so in this case, we enter Bronsted-Lowry. These are two separate people who came together to figure out the next definition of what an acid and base could be. And we kind of need to look at both of them at the same time. Okay, so if we go back to or HCl. Okay. And this time let's put water in. Okay. I've shown you this reaction before where if you put water, you will get the hydronium ion as well as your chlorine ion. Okay. And we have said in the past that your H3O plus and your H plus are virtually identical. Okay, they both represent the active component of an acid. Now, here we really see how acids and bases behave. So, for example, in order for this HCl to become the products that are listed on the right-hand side, this H, okay, the H plus must be donated, okay, in order for Cl to form. So here we say that HCl donates an H plus ion. Okay, now the H plus ion is actually the same thing as a proton. Because when you look at a hydrogen atom, one single hydrogen atom has one proton, one electron. So if you take away the electron and you're only left with a proton, that's your H plus ion. Because hydrogen doesn't have a neutron present. So this is the only substance that can do this. So when we're talking about H plus ions, we're actually talking about protons. So either way, this acid donates an H plus ion or proton. So basically what Bronsted and Lowry are saying is that a Bronsted-Lowry acid is a substance that can donate a proton, which is your H plus ion. So in terms of bases, this is helpful for us because in terms of bases, it's not about whether or not you form OH ions, but if we're looking at the perspective of a proton, okay, every Bronsted-Lowry base does the opposite of what the acid can do. So if the acid can donate, a base would accept. So in this case here, we can go back to our carbonate ion. Okay. So if we were to give carbonate, let's say 1 proton, it would now become HCO3 negative. So let's put in all the states for all of our ions here. So by this definition, what we see is that we see this H plus ion being accepted by the CO3. Okay, so carbonate accepts a proton. So anytime you see a substance accepting a proton, it's considered to be a Bronsted-Lowry base. So a Bronsted-Lowry base is a substance that can accept a proton. From another substance. So the beauty of this particular definition is that it doesn't really change how we look at acids, but it expands on how we look at bases. Okay, so note all Arrhenius acids are Bronsted-Lowry acids, but not all Bronsted-Lowry bases are Arrhenius bases. We do need those two definitions of bases in order to describe the majority of bases. Okay, so again, Bronsted-Lowry acids donate protons, Bronsted-Lowry bases accept protons. And all of this would have been okay if it weren't for another substance. Okay, so I mentioned at the beginning that we have 3 different definitions for acids and bases. Well, here comes the third one. And this third one deals with our good friend Lewis. These are Lewis acids and bases. Okay, it's the same Lewis from our Lewis dot diagrams. So naturally, we're going to use a few Lewis dot diagrams to help us explain how these acids and bases work. So the one type of substance that doesn't fit in with either Arrhenius or Bronsted-Lowry is this guy here, NH3. When you look at NH3, it looks like an acid. Okay, so it looks like an acid because it has a whole bunch of hydrogens, but it does not behave like an acid and does not have the pH of an acid. So it is a base. But here's the thing, neither Arrhenius or Bronsted-Lowry could figure out why it is a base, because neither of their definition would explain how NH3 behaves. So NH3, most of you should already know, is the same thing as ammonia. Okay, it is a very strong base. Okay, so it's not just the base, it's a very, very strong base. So to help us figure this out, Lewis figured out a couple of things. Okay, so I think it's better for me to describe the definition here of a Lewis base first and then show you the example. Okay, so a Lewis base is a substance that can donate a pair of electrons. Okay, so we're not talking about protons anymore. We're talking about a pair of electrons. So what that means for the acid is a Lewis acid is a substance that can accept a pair of electrons. So one donates a pair of electrons, the other accepts a pair of electrons. And the best way to observe this is, again, to look at ammonia as our example, and to look at how the Lewis bases are in terms of a Lewis dot diagram. So we've drawn out ammonia a couple of times, but this time around, I'm just going to draw in a different way just to show. So nitrogen contains 5 valence electrons. Okay. You have 3 hydrogens, and they have a shared bond like this. Okay. So these are your normal regular covalent bonds. But nitrogen has a pair of electrons that solely belongs to itself. Now, because this is a base, we can identify this right now as a Lewis base. Okay. And according to Lewis bases, they're willing to donate a pair of electrons. So the pair of electrons that they're going to donate, as you would already suspect, is this pair right here. You have a pair of electrons that ammonia is willing to donate to another substance that perhaps is looking for a pair of electrons. So to find a Lewis acid, okay, you're very limited in terms of how many Lewis acids there are. Okay, so here we're going to look at boron, bonded to 3 fluorines. Okay, boron is the only non-metal member of family 3A. Okay, so it will gain electrons instead of lose electrons to complete its octet. So if we have boron with 3 fluorines, each of them having 7 valence electrons, then you get this scenario here. Okay, so boron trifluoride requires 2 more electrons in order to be stable. Okay, the Lewis base has 2 to give. So this is my Lewis acid. It wants a pair of electrons. Okay, because right now this boron only has 2, 4, 6 valence electrons. It needs 2 more to be stable. So literally speaking, when you have these 2 molecules together, boron will come in and they will want to bond with that nitrogen. Okay, so nitrogen and boron must therefore form a coordinate covalent bond between them. Okay. So what we see happening is interactions between Lewis acids and Lewis bases generally forms a coordinate covalent bond. So now we have basically 3 separate definitions for acids and bases. Okay, we've gone from very simple definitions of an acid and base to a moderate definition that's a little bit more involving with protons, to finally a more complicated way of looking at how acids and bases interact in the form of Lewis acids and Lewis bases. So hopefully this isn't too confusing. For the most part, once you understand the 3 different types of definitions for acids and bases, they're pretty much the 3 that we use to describe how most or all acids and bases function. Okay, they each, well, every substance falls into at least one of these 3 types of acids and bases, if they are acids and bases. Okay, so try to keep that in mind, because we do have other substances that are neither acids or bases, and therefore they don't apply to these 3 definitions. But if you do have an acid or a base, they will likely fall into one of the 3. So to summarize, Arrhenius, acids, and let's say bases. These guys produce H+, and the Arrhenius bases produce OH negatives. If it's Bronsted-Lowry, we're talking about accepting, we're talking about donating H+ ions, and the bases accept H+ ions, while Lewis acids and bases, okay, the acids accept a pair of electrons, and the bases donate a pair of electrons. Okay. So between the 3, if I give you any acid or base, you should be able to figure out which type of acid or base is present, whether it's Arrhenius acid or base, a Bronsted-Lowry acid or base, or Lewis acid or base. Well, that's all I have for today. I hope to see you guys soon.